over the past 2 decades, the International Space Station has taught us one important lesson. Collisions with micrometeorites are completely unavoidable and happen all the time. And we've discussed some of them, some of the bigger ones, here on the channel, even as recent as just a few months ago. Which is exactly why, when the scientists were planning the James Webb Telescope mission, they've anticipated the amount of various collisions the telescope is going to be receiving over the next few years. And so the original designs of the telescope anticipated a lot of the changes over time and the degradation in the quality of the images because of the collision with various tiny pieces of rock, various micrometeorites. But what the scientists did not anticipate is a slightly larger in size micrometeorite that actually did collide with a mirror only a few months ago. Hello wonderful person, this is Anton, and today we're going to be discussing yet another part from the report that was recently published, and that as always you can find in the description below, that goes through some of the more detailed analysis on the somewhat unexpected effects the recent collision had on the main mirror. In other words, even though the scientists anticipated at least one collision per month, that's slowly going to degrade the mirror over time, this right here seems to be an outlier, and it's a much bigger outlier than anyone predicted. And so let's discuss this in more detail, talk a little bit more about the facts about these collisions, and what the scientists are going to be doing in the future to prevent this from happening. So first of all, we know that this particular collision did not really affect the telescope that much. These images that were recently received, the images we discussed on the channel several times now, were essentially produced after this collision, which implies that the telescope still functions as intended and is going to be working as intended for many months and many years to come. We also know that since the original launch a few months ago, the telescope has already received at least 19 tiny collisions from various micrometeorites smaller than a grain of sand in size, with 6 of them leaving marks behind which are slowly causing the effects on the telescope, but not dramatic enough to change anything for the next few years. Nevertheless, it means that at least once a month there's going to be one collision somewhere on a telescope. Very likely similar to what you see right here, leaving just a small mark behind, but over time this might actually start adding up. And so if the mission lasts for at least 10 years, we can expect at least 100 of these collisions, and very likely a lot more. But when the NASA engineers were building the telescope, they've conducted very thorough tests on the mirrors, even hitting them with various samples, simulating various collisions from micrometeorites. In other words, these collisions were expected, and the telescope was tested before it was even launched. On top of this, the design itself involves materials that generally withstand extreme pressures and temperatures really well. For example, the individual pieces of the mirror are actually made out of beryllium, a very light and a very strong material that's usually used in aviation for various supersonic flights and has even been used in space shuttles, with the rest of the mirror designed and polished so extremely well that the telescope actually has accuracy much higher than needed for the actual mission. Or in other words, it was designed to actually be a little bit more accurate than it needs to be. And so over time, even if the micrometeorites degrade the quality and the accuracy of the mirror itself, it's still going to be producing really good images because the engineers in this case kind of over-designed it. And so until that major collision that happened a few months ago, none of the other collisions affected anything. But between May 22nd and May 24th, there was a very unexpected and somewhat large collision in the segment known as C3. A collision that seems to have affected the performance way more than anyone expected. And in this report we even get the actual numbers and the actual visual representation of what all of this means. So in terms of the accuracy of the mirrors, the performance of the telescope is measured by the amount of various deformations from all of the starlight hitting the telescope, with the smoothness of the mirror being responsible for the accuracy. So if the mirror is extremely smooth, as it was originally, the amount of deformation of the light is only going to be in like 5 to maybe 10 nanometers in size, which is just a little bit thicker than the thickness of the DNA molecule. And so when this mission began, the level of wavefront error was approximately 56 nanometers. You can kind of see that some of the mirror segments had a slightly larger error, but the majority were more or less the same. But following the impact on May 22nd to May 24th, the error jumped up by about 5 times. Right after the impact, it was approximately 258 nanometers, which was much higher than anticipated even after years of operation. But because we have 18 mirrors, it is possible for the scientists to average all of this out, and it's also possible to move each of these segments individually, readjusting and averaging out the overall errors. And so following a major readjustment, they were able to reduce the error in the C3 mirror down to 178 nanometers, but still approximately 3 times higher than it was before. And unfortunately, this also decreased the overall capability of the telescope by a tiny amount. Right now, they believe that the average error has increased to approximately 59 nanometers, which is about 10 nanometers above the previous average that the telescope was experiencing. Which is of course why it was possible to produce all of these beautiful images, and why the telescope is still going to be functioning for many years to come. But there is of course a small concern here. The concern in regards to this particular impact. Because of the size of the particle and the speed with which it was moving, it's currently completely unexplained. Based on previous statistical analysis, nobody expected such a large piece to ever affect the telescope, especially so early on. And since James Webb is orbiting pretty far away from anything, and we don't really expect a lot of fragments or a lot of pieces of micrometeorites in this region, it adds a little bit to the mystery of what exactly caused this, and also raises a few questions about this particular environment and where all of these fragments are coming from. For all we know, maybe these Lagrange points, the stable points of orbit in the solar system, tend to capture other stuff, such as micrometeorites, which can then maybe collide with various missions that are also in this region. Or maybe there is a population of an unusually large micrometeorites that we never really knew about or never knew existed, and some of them might actually be in this region as well. And since the previous collisions with smaller objects have only decreased the overall error by about 1 nanometer, the fact that this one collision managed to take this mirror all the way to 250 nanometers of error is definitely completely unexpected. And so the question now is, well, was it just an unlucky event? Or is this something that's going to happen again? And if it happens again, it means that the scientists will need to recalculate the overall number of collisions we usually expect for various interplanetary missions. That of course also includes a potential Martian mission, which might even have astronauts on board. In other words, this is actually really important for any potential crewed mission that might one day visit other planets. Which also means that the James Webb Telescope has officially now acquired a new mission, measuring the number of impacts of larger pieces in this particular region. Chances are that even after a few of these collisions, it's still going to function and it's still going to be producing beautiful images, but calculating the number of these collisions and more importantly, figuring out if this is going to be a problem for other missions, that's of course something that the scientists did not really anticipate originally. But despite all of this, the observatory is still working fine. As a matter of fact, it's working better than expected. With this report even mentioning that there were actually 344 different points of failure that were anticipated by the engineers and the scientists, with most no longer being an issue, with the majority of the problems related to various instruments. But chances are, even if one of the instruments fails, the mission is not going to stop. As a matter of fact, the telescope includes a lot of redundancy and can actually operate even if the majority of the instruments and the majority of the parts fail for one reason or another. So yeah, this mission has been designed pretty well. Which is a bit of a contrast with the original Hubble telescope launch, which created a bit of an embarrassment for NASA, because for the first few months, the telescope was unable to produce clear images. This was a bit of a failure. James Webb, on the other hand, is almost the opposite. And so really the only issue the scientists have faced so far is this unusually large collision, which nobody anticipated. And so because of this, the scientists are now planning for the telescope to avoid these during future passages through, for example, various micrometeorite dust fields that often cause meteor showers on the planet. And so during that time, the scientists think they can actually turn the mirror itself, pointing it sideways toward the direction of movement, in order to avoid future damage or direct hits from various micrometeorites. But for now, for the next few months, nothing major like this is going to be conducted, and the scientists are just going to wait and see if maybe, just maybe, this particular collision was just an anomaly. It might never happen again, and the telescope might only receive the expected one collision per month. A tiny collision that's only going to decrease the overall sensitivity by just 1 nanometer. But I'm sure we'll have more updates before the end of the year, and so I'm going to be following this up with another video sometime soon. Subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, and support the channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.